Okay, everyone, let's get started. So yeah, today we are starting a new chapter, chapter 5, orthogonality. And so basically this is now we want to talk about geometry of our linear spaces. Okay, and let's start building from linear spaces that we are more familiar with. That's those Euclidean spaces Rn or R2 and R3. Okay. And what we are doing is we are going to show all the geometric concepts that can be derived from this definition of a scalar product. Okay, and so a bit of a spoiler ahead. Later on, we'll define all the concept. We will define the scalar product for every abstract linear space. I guess not every, but for a lot of abstract linear space. And then we can define concepts such as distance, angle, and projection for abstract vector spaces. Okay. But for now, we define, I guess we review the idea of the scalar product. And the scalar product for two Rn vectors. So we have one n-dimensional vector x, another n-dimensional vector y. And we define their scalar product or inner product as this way. And we write it in this form because we can think x and y as two n by 1 matrix. Then if you transpose x, then it becomes a row vector. And then we write y is a column vector. Then x transpose times y, we can just think of this as a matrix multiplication. Then it gives you a 1 by 1 matrix, which is just a number. And if you look at the element of this matrix, is x1, y1 plus x2, y2 plus all the way to xn, yn. Okay? So it just sum together all the product of each individual elements. Okay? And yeah. So this is our definition of a scalar product on two vectors in Rn. And there is some technicality with how we define the space of those things. But basically, for now, we define scalar product between two column vectors of Rn. And when you do the product between them, you need to do transpose on one of the vector and multiply on another vector. Okay. And yeah, the details are not too important. But the result of this scalar product is important. You need to know you have two Rn vectors, scalar product is this thing. Okay? And let's see some example. This is quite straightforward. You have x, y. X is 3, 2, 1. Y is 4, 3, 2. And when you do scalar product, you just multiply each dimension together and add them together. So you have 3 times 4 plus minus 2 times 3. Plus 1 times 2, so it's 12 minus 6 plus 2, and it's 8. Okay, it should be quite straightforward. Okay, and yeah, so now we are going to define a whole bunch of geometric concepts with from scalar product. Okay, so let's go back to R2 and R3, where we are very familiar with all the geometric concepts. Okay. And first thing we define is distance or length. Okay. Okay. So how do we define length in R2 and R3? By saying scalar product is we say when we have any vector, okay, and then its distance can be defined in terms of our scalar product. Okay. And what's our distance? So or length of a vector. Length of a vector is just the square root of of the vector scalar product with itself. Okay? So we take this xtx. This is a scalar product. Then we take a square root. That's the definition of our length here. Okay? And let's see that this works out as okay, so this should be definition here. Okay. So length of any vector is a square root of the scalar product of it with itself. And we see that we write down the formula. Then if x equal to x1, x2 or x1, x2, x3 when they are in R2 or R3, then you work out the formula. You see that this is a square root of x1 squared plus x2 squared, or square root of x1 squared plus x2 squared plus x3 squared. and you see that this is this matrix with our usual definition of length in Euclidean space. Okay, so you see those Euclidean lengths in R2 and R3 can be defined in terms of just scalar product. Okay, and okay, so any questions so far? This is defining length in terms of scalar product, and then we will. Okay, so this is length. Then, as we said, the next thing we define is angle. Okay, and we can define angle between two lines by also scalar product. I guess this is yeah, we will do the definition later. But let's look at the concept of angle first. Okay, so if you have a vector x and a vector y, then we can think of vector x is some line or going out from origin to the end where x1, x2, and vector y is another line going out from 0 to y1, y2. Then you can think about the angle between this line and this line. You have the angle between those two vectors. That's the angle between those two vectors. And we can also have the distance between those two vectors should be the length of this vector. That's just the y vector minus x vector. Okay. So if you write down those two vectors on a plane, then you can have also a vector on this edge of this triangle. And this will, if you go from this end of x to end of y, then this vector will be the vector y minus the vector x. Okay? So the distance between those 2 points should just be the length of this y minus x vector. Okay? And yeah, so we have the distance between two vectors is defined by the length of the length of x minus y, and once again, this is the length is defined by scalar product. So the length is length of x minus y equal to square root of this x minus y transpose then times x minus y. So the scalar product between x minus y and x minus y. Okay, and also something you can derive very easily is that x and y is symmetric here. So the length of x minus y, which is the length of this vector, from here to here. Sorry, this is y minus x, and so the length of x minus y should equal to the length of y minus x. So whether the vector is this direction or this direction, it should have same length geometrically. And you can also do algebraic derivation. Very easy to see that x minus y and y minus x has the same length. Or when you have x and the length of x equal to length of minus x. Okay. That's something. Okay. And here we use the fact that the length of x will equal to length of minus x. Okay, and let's see some example of calculating the distance between two vectors. It's quite straightforward. You have x equal to 3, 4, y equal to minus 1, 7. And then you can have y minus x equal to just subtract each coordinate. So it's minus 4 and 3. Then you have the length is the length of this vector, and it's you have the 3, 4, 5 relation. So its length is 5. Okay. And yeah, so this is length between, this is the distance between two vectors. So this is once again about length of some vector. Distance is the length of the difference. And finally, we can talk about angle. So we will say we want to know angle. Okay, and angle between two vectors can be defined this way. Okay. And if you really want to calculate it, you need to do arc cosine. But we can calculate the cosine of the angle between two vectors. Okay, so we have that if we have, and I guess the thing we kind of want here is cosine theta will equal to length of x, length of y divided by x inner product with y. And yeah, so this is a geometric view here. So we have the vector x here, the vector y here, and the angle theta here. So then we say the cosine of this angle theta will equal to length of x, length of y divided by the inner product. And I think this is something we learned in high school, but because in high school you learn the inner product. Yeah, in high school you kind of derive this, but let's do this once again. And yeah, so we use well, another theorem that we haven't proved, but we use geometry theorem to prove this. It's a bit of cheating. There are a whole bunch of ways to do this, but we choose to do this way. Okay. And yeah, we use the laws of cosine. We say the length of this thing equal to so we look at this triangle and we use the law of cosine. So we say length of y minus x squared equal to length of x squared plus length of y squared minus 2 length of x to length of y and the cosine theta. Okay, so here we see how we get our xy cosine theta here. Okay. And yeah, so we can have xy cosine theta being some linear combination of these terms. And now the only thing we need to do is expand out this length of y minus x. And as we said, length of y minus x can be written in terms of inner product. So it's the inner product between y minus x and the y minus x. Okay. And then now in this inner product, we just use that inner product is well, matrix multiplication. So it's very linear. It has you can use a whole bunch of linear laws of matrix multiplication, and we see that well, YTY. Then this is we have a distributed rule for matrix multiplication. So you have two terms multiplied by multiplying two terms. Then we have 4 terms here. So we have y term and xy term, and yy term, and yx term, and xy term, and xx term here. Okay. And then we see we have a whole bunch of cancellation here. So yy term cancel with y length of y squared because they are same, and the xx term cancel with x terms. Okay. So we are just left with this yx term and the xy term. And here we use the fact that y inner product with x will equal to x inner product with y. Okay? And this you can just check by definition. So let's go back to our definition slide. So if you look at all the coefficients of inner product, then x inner product with y will equal to y inner product with x, because for each individual term here, x times y, x1, y1 equal to y1, x1, etc. Just multiplication is commutative here. Okay. And yeah, so inner product we also have this property. And yeah, in here we use a whole bunch of property without proving it, but those are easy to show property. So here is another property of inner product: x inner product with x, x inner product with y equal to y inner product with x. Okay. And from here, so we are left with these two terms, and yeah, we see we have twice x inner product with y, and that's then multiplying with 1/2 is x inner product with y. Okay, so that's how we get the angle between two vectors, or the cosine of the angle. But the other way to interpret this theorem is this is another definition of inner product. So I guess we can also view this as a geometric interpretation of inner product. It's this vector, those two vectors, and their length times the angle between them. Okay, so when you, I think this is something we learned in high school. So when the two vectors are really similar, their inner product is larger. If they are in the same direction, the inner product is the product of them. Okay. So we have if the two vectors are same direction, inner product is just the product of the length, and then also special case we want is when the two vectors are orthogonal, then the inner product is 0. Okay. And yeah, so here is where we get the idea of orthogonal. So if the cosine theta is 0, then inner product will be 0, and that's when the two vectors are orthogonal. Okay, and yeah, before that, let's talk about another concept. So now we have the concept of unit vector. And yeah, what a unit vector is just a vector of length 1. Okay, so I guess we should have say here unit vector. Unit vector is just a vector of length 1. And how we get a unit vector from any vector is we just have a vector that divided by its length, then we will get a vector of length 1, and with the same direction of x. Okay. And yeah, that's a unit vector. Okay. And there are a whole bunch of nice expressions we can say unit vector. Okay. And so we can use the unit vector to express this cosine theta between vector x and vector y a little nicer. So we have two vector x and y. We can calculate the corresponding unit vectors. So x we can calculate unit vector u, y we can calculate the unit vector v. Then the angle cosine theta between x and y will be the inner product between those two unit vectors. It will be u inner product with v, or utv. Okay. And that's because cosine theta, as we say, is x inner product with y divided by length x, length y. Okay. Oh, here I have the wrong writing. Sorry. It should be the other way, the up and down. So cosine theta equal to x inner product with y and divided by length x, length y. Okay. And yeah. Okay. So we do the division, and then because we know inner product is just matrix multiplication, so it's linear in x and linear in y. So when you have a linear product, inner product divided by x, then it's this x divided by inner product divided by some alpha, then it's equal to x divided by alpha times y, or x inner product with y divided by alpha. Okay. And so you can have this x go to dividing this x vector, then you can have this length y dividing this y vector, then it becomes unit vector of x and a unit vector of y. Okay. And yeah, so here we have a nice expression for cosine theta. It's a unit vector inner product with another unit vector. Okay. And once again, we can see some examples. So x is this 3, 4 vector, and y is this -1, 7 vector. The unit vector for x is 3 over 5, 4 over 5, and the unit vector for y, the length of y is more complicated, is 49 plus 1 equal to 50, is square root 50. So you can -1 over 2 square root 2, -1 over 5 square root 2, and 7 over 5 square root 2. And cosine theta is just this inner product with this, so you have a whole bunch of multiplications. So the denominator will be 25 square root 2, and up here you have -3 plus 28, so it's 25 here, and 25 cancel out. We have a nice answer, so it's 1 over square root 2. Okay. And cosine theta is 1 over square root 2. Then you can try to do our cosine, and it should be 45 degrees over pi over 4. Okay, so yeah, that's the example. Okay. So you see that you can calculate the angle between those two vectors by calculating this inner product. Okay, and yeah, so that's example 3. And then we have this nice inequality, that's Cauchy-Schwarz inequality. It can also be written in terms of inner product, and they just say inner product of any two vectors in R2 and R3 is less equal to length of x and times the length of y. Okay. And yeah, and it can be easily proved by just seeing the inner product between two vectors is the length of x times the inner length of y times the cosine theta. and basically you take the absolute value of two sides, then you see that this must be less than equal to this side, because this must be less equal to these two things, because the absolute value of cosine theta is less equal to 1. Okay? And you can also have if only if condition here. So if one is cosine theta equal to what, absolute value of cosine theta equal to 1, then you want the u inner product with v equal to 1 or minus 1, and yeah, and that can only happen. I guess the either way to see is this cosine theta. Okay, so we want this equality to hold. That's when cosine theta equal to plus minus 1, and that happen when theta that happen when this is if only if theta equal to 0 or pi. So x and y are in the same direction or opposite direction. Okay, and or that means the vector is one of the multiple of each other. Okay, and oh, I guess that's one condition. And another condition is when x or y is length of 0. Okay, so you have length of 0, then both of this and this are 0. Okay, so that's Cauchy-Schwarz in R2 and R3, and then we have finally we have orthogonal. Okay, and orthogonal, as we say, is just theta equal to pi over 2, and then we know that. So when we have two vector orthogonal, that's when theta equal to pi over 2. That goes to cosine theta equal to 0, and this will be xty equal to 0. Okay, so that's orthogonal. And once again, we want to define everything in terms of inner product. So we define orthogonal as inner product equal to 0. Okay. And yeah, so that's the definition of orthogonal in terms of inner product. Okay. And we have a whole bunch of examples of orthogonal vectors. Okay. And so first is that special case, the vector 0. So actually, this is quite weird. So this is something we cannot quite see in geometry because we don't have a line of length 0. Okay, but in terms of a vector, we can have a vector of length 0. So this 0 vector, which is just okay, so let's write it down. Okay, so in R2, the 0 vector is this two-dimensional matrix, or this 2x1 matrix with 0, 0 component. Okay, and by our definition of orthogonal, if you try to have this inner product with anything with R2, you get 0. So the 0 vector is actually orthogonal to every other vector. Okay, so this is a special case. Okay, and we have a more common case. So we can have this vector 3, 2 and a vector minus 4, 6. And the inner product will be 0, and they will be orthogonal to each other. So inner product will be minus 12, then plus 12. Okay, and we can also have a 3-dimensional case. So the vector 2, minus 3, 1, and the vector 1, 1, 1 are orthogonal to each other. So we do inner product is 2 plus minus 3 plus 1, and it's equal to 0. Okay. Any question? And yeah, so now we have defined distance and angle on inner product, and because we define angle, then we also define orthogonal. Okay, and we see that orthogonal in terms of inner product has this very easy definition. Okay, and then we go to the most complicated concept, the geometric concept, and its projection. Okay, so we have two vector x and y in R2, R3. Then we can think about projection of x onto y, and we define two different projections. We have a scalar projection and a vector projection. And I think a vector projection is more straightforward. So the projection of this vector x onto the vector y is this vector p here, where p has the same direction as y. So this is the projection part, and also it's it's a difference between x and p is orthogonal. So x is decomposed into this projection part, which is same direction as y, and the remaining part, which is orthogonal to y. So we have this z equal to x minus p, and so the important thing of projection is z and p should be orthogonal. Okay, so we should have the inner product with p equal to 0, should equal to 0. Okay, and yeah, so this is projection, and so p is called vector projection, and we also have the scalar projection, which is just the length of p. So we say p is some alpha times the u, where u is just a unit vector for y. Okay, and now we want to have, so this is a geometric view of the projection, and now we want to calculate alpha and p in terms of inner product. Okay, and okay, so first we have alpha, and yeah, so u is the unit vector of y. Then we can we want to have alpha such that p equal to alpha u is also going to z equal to x minus alpha u. Okay, and anyway, so here we have two derivations. One is a bit of I guess a bit of cheating. So we have alpha equal to x cosine theta. This is just from geometry, because from geometry we know this length alpha. We have this triangle here. We have x and this then this line and then this line, and by trigonometry we know the length of this length of this edge here is just cosine theta of length of this edge. So alpha equal to x cosine theta, and that should equal to, now we can now we try to write things in terms of inner product. Then we have we just multiply upper side and lower side both by y. Then we can have, because we want xy cosine theta here, then xy cosine theta we know is x inner product with y, then it's divided by y. Okay, so this is the geometric derivation. And then if you want more algebraic derivation, we can do it here. Then we start with the condition we want. We want u inner product with z equal to 0. Okay, so we have a u inner product with z equal to 0, and then you can write z equal to z in terms of u once again. So x and u. So z is x minus alpha u. Okay, because this is the definition of z. Okay. And now we multiply all this inner product here. So this is utx times minus alpha times utu. But u is a unit vector, so utu is the length of u should become 1. So this is just minus alpha here. Okay, so in the end, we have 0 equal to utx minus alpha. Okay, and so this tells us what's alpha. Alpha is utx or xtu. Okay, and it's the same as here. If you just combine those two y, so yeah, so alpha is utx basically, okay, or xtu. So any question? So that's how you calculate alpha. And so alpha is a scalar multiplication, scalar projection, and we can also have the vector projection. Then you just multiply alpha back with this u. Okay, so p is alpha times u, and u is y divided by y length, and then you can have a quite complicated formula for u in terms of inner product between x, y, and the length of y. Okay, so this is alpha is what we have here, xty divided by length y, and u is y divided by length y, and yeah, so everything together here is so the actual only vector part is this y, although you see a lot of x and y, but the only vector part is y. So because remember, p should be a vector that has y direction, so it should be y multiplied on side number. So we have y here, y here. So you have a y vector here, and the other things are just number, and those number are and those numbers are x inner product with y and divide by length of y squared. Okay, and if you want to write things more in terms of inner product, then you have this vector y and multiply length being inner product or between x and y divided by inner product between y and y. Okay, and that's a formula. And okay, and here we give so if you think this is a bit complicated, although it's okayish. Another nice way to memorize it, I think, is you can also go with this in terms of u. So, okay, so here is a form that a form of a projection that more emphasized that is in y direction. And then you can have this as another form that's more more emphasizing that is some projection from x, that is you start from here. So you have once again p is alpha u, and well you can multiply alpha is a scalar, so you can put this scalar. You can think about multiplying scalar as a matrix multiplication with 1 by 1 matrix, and you can put this 1 by 1 matrix after u. Okay. And so you can pick UTX here. So P is U times UTX as a scalar, as a matrix multiplication. Okay, and why is this UTX as a nice form? Because you can think about this as I guess I should write still write one in the middle. So this is UTX. So this is just a matrix multiplication. Because UTX is a 1 by 1 matrix, then you can multiply your n by 1 matrix multiplying a 1 by 1 matrix. Okay, and if you put this form, then this is a form that's more obvious that you are doing a linear operation on your input on your matrix on your vector x. Okay, so you can also think projection as some linear operation on your vector x, and the linear operation is you multiplying with this matrix UUT. Okay, and yeah, so UUT is I guess it's a projection matrix, and it's if you think about a matrix, it's a projector onto this U vector. Okay, because you multiply this UUT on any vector, then you will be a vector on this u direction. Okay, and yeah, so here we have example of a projection matrix. Okay. It's I think it's a bit simpler than this form, okay. But yeah, but this you might need to do a bit of extra calculation. You go to calculate u, and those two formula are more direct. More directly from the vector x and the vector y. Okay, any question? If not, then yeah, let's see some example of calculating projection with inner product. Okay, so we have yeah, this is a direct example. We have x being this 1,4 vector, and I guess y we don't have a vector. Y we are saying we have a line, and we can give a line equation. We have a y equal to 1. Y equal to 1 over 3x. Okay, and then we can find a vector here, because y equal to 1 over 3x. We can find a whole bunch of points here, and I guess the point we can find is maybe x equal to 1, y x equal to 3, then y will equal to 1. So we can have this 3, 1 point that's on this line. Okay, and so we will do this by have this 1,4 project on 3, 1. Okay. So W equal to 3, 1, and V equal to 1,4, and yeah, we can find the vector projection. Okay, yeah, vector projection point Q here, and this projection point Q. Then we just go with this formula. So we have V inner product with W, and we should have direction W. So V inner product with W, then W inner product with W. And V inner product with W, we have 7. W inner product with W, we have 10 here. So this 7 over 10 times W, and 3, 1, and it's 2.1 and 0.7. Okay, should be quite straightforward. Okay, so we can calculate the projection point to a line, and if the line is going through the origin, because we can find the vector on the line easily, and we have a projection of vector onto vector. Okay, and then we can also have we have a bit of notation. We have 2 points in 2-dimensional or 3-dimensional space. We can have a vector from P1 to P2 by determined by this notation. So P1 to P2, okay, P1, P2 vector. And then now we try to describe a plane in a 3-dimensional space, okay. And so if we have so we can define a plane by a vector and a point, okay. And I guess do we have a picture? We have a bit of a more complicated picture, but we can use it here. Okay, so we say we have some direction of some vector and some point on 3-dimensional space. We can define a plane that's the set of all points where you have some P1 to this P0, and or P0 to some P1 that's orthogonal to this normal vector. Okay. So we can define a plane in 3-dimensional space by a vector and a point, and you have the plane is collection of all the points where those points to your starting point P0 is orthogonal to your vector. Okay, so that's how we can define the plane to with a point and a vector. Okay. And as we say, we want so we found the plane, and we say so now we have another name for orthogonal. So we say the vector n and the plane is normal to each other. Basically means orthogonal to each other. Okay, and and now we can solve the equation for this plane. We want P0P. Inner product with n to be 0, and if n is some ABC and P0 is x0, y0, z0, and I guess we skip calculating the vector P0, but the vector P0 will just be x minus x0, y minus y0, and z minus z0. Okay. And when you take inner product, you have a x minus x0 plus b y1 minus y0 plus c z minus 0 equal to 0. Okay, so here we derive the equation of the plane described by this normal vector n and some point x0, y0, z0. Okay, and we can also rewrite this equation a little bit to a more familiar form of plane equation. So we can have ax plus by plus cz equal to this just a number ax0 plus by0 plus cz0. Okay, so we I think in high school we learned that the equation for a plane is x plus by plus cz equal to some d. So just some linear equation on x, y, z. Okay, and so this is a plane, and we can have a very direct example. So we have vector n equal to 2, 3, 4, and the point P0 equal to 2 minus 1, 3. Then we can have the equation of this plane is 2 times x minus 2 plus 3 times y minus 1 equal to plus 1, minus 1 equal to plus 1, and plus 4 z minus 3 equal to 0. Okay. Okay, and so here with the inner product we derive the plane equation, and we can calculate a more complicated example from this plane equation. So we can try to find the distance of a point to a plane, and I guess here we have an easier example when the plane passes through origin. Okay. We have the plane is x plus 2y plus 2z, and then you can see that because d equal to 0 is a plane that goes through origin, and it's just plane goes through origin with no vector being this 1, 2, 2. Okay, and now the projection onto this plane can be just done by So now we want this 2, 0, 0 vector to be to find its distance to this plane. Then by looking, now we think about a little bit of geometry. We see that the distance to this plane that goes to 0, 0, 0 should be just the projection onto this normal vector. Okay, and because this distance equal to this distance. Okay, and now we just do projection of this vector onto this vector, and yeah, and that's what we know. So it's this n vector multiplying with inner product between n and v divided by length of n. Okay, so inner product between n and v is yeah, I think it's a bit wrong. Oh, sorry, we want the distance of the vector. Okay, so the distance of vector is we want the scalar distance. So distance of vector once again is just an inner product between n and v divided by the length of n. Okay, and so length of n is the square root of 1 square plus 2 square plus 3 plus 2 square, and we have an inner product between n and v is 2, and then it's 9 here, so it's divide, taking square root becomes 3, so it's 2 divided by 3. Okay, and yeah, so that's an example, and it's a bit easier because the plane goes through 0, and you can think about how you do this when plane don't go through 0. It's more complicated. Okay, and finally, in the last 10 minutes, we want to talk about, I guess, the more important thing. So so far it's a bit of I think it should be a review for your high school geometry, but writing all things in terms of inner product. And because now we write everything in terms of inner product, we can define all the similar concepts in terms of Rn, and later on we will define those for abstract vector spaces. Okay, and yeah, so geometric now we have a geometric concept for Rn. This is something you might learn in your high school. Okay, and it's just basically we just generalize everything in terms of inner product. So first we have inner product in Rn, and we already define inner product in terms of this matrix multiplication, and it just works out. So inner product, oh sorry, we already define inner product for Rn because it's a matrix multiplication. And now we can define length for Rn. Once again, it's a square root of inner product of the vector with itself. So it's the square root of all coordinates squared, square root of all coordinates squared, and so on. Okay? And this should seem like a quite straightforward generalization. So just square root of x1 squared plus x2 squared all the way to xn squared. Okay? So we can define length, and we can define distance. So distance is once again just this length of vector y minus x or x minus y. And you can easily show that the Cauchy-Schwarz inequality will also hold. Okay. Okay. So Cauchy-Schwarz inequality will also hold. I guess here is we don't quite have a geometry yet. So to prove this, you need to go back to actually algebra. But we just state that it holds. So the absolute value of x inner product with y divided by x length y length will be less than 1. Or other way to say this is inner product of x and y divided by length x length y is between this minus 1 and 1 range. Okay, and anyway, so this is the distance and the Cauchy-Schwarz, and we also have angle. Okay. And now the angle is really defined by inner product because we don't really know how to draw things in Rn, but we can still generalize the definition of angle in terms of inner product. Okay, so angle cosine theta is defined by x inner product with y, then dividing length x and length y. Okay, so here we have the definition of angle in terms of Rn. In Rn, in terms of inner product, so it's a bit important here. Okay. So the cosine theta is x inner product x divided by length x, length y. And you can also define this in terms of unit vector. Unit vector is still easy concept. So x divided by length of x, y divided by length of y. Then cosine theta is just UTV. Okay, and yeah. And once again, this is all defined in terms of inner product because the length is also defined in terms of inner product. Okay. And yeah, so cosine can be computed through this scalar product. And then we can also have the concept of orthogonal, just when concept of orthogonal is when is theta equal to pi over 2, cosine theta equal to 0, and that's when x inner product of y equal to 0. Okay, and sometimes we use it with the perpendicular symbol to mean to the vector orthogonal, and we'll write it in this way. So x perpendicular y means x inner product with y equal to 0. Okay, so this is extra notation. And also we have vector and the scalar projection, and we don't write down detail. I guess we can write a little more. So we can have, so once again, alpha equal to UTX, UTX, alpha equal to UTX, and P, so these two are vectors, P equal to UT, sorry, too many vector signs, so I changed my mind, so don't write vector sign. So P equal to UUTX, okay? And yeah, so those vector, these basically vector, basically inner product between vectors and vector multiplication. Okay? So UTX is the inner product between U and X, and P is just U multiplying UTX. Okay, and but in this form, you can also think about this as a matrix multiplication. Okay, and but now U and X can all be n-dimensional vectors, and so you can calculate the scalar and vector projection in Rn just in this form. Okay, and yeah. Okay, and I guess also something nice is we can have Pythagorean law in Rn. Okay, so we think about the length of x plus y squared. Right. So we have two vector x and y. Then you can think about length of x plus y squared and see a geometry first. So we have x here and y here, and this vector will be x plus y. And the length of x plus y squared, and we calculate this all in terms of inner product, will be x plus y, inner product with x plus y. And you multiply everything out, and you have x inner product with x, y inner product with y, and 2 of x inner product with y. And when x inner product with y equal to 0, then it's just equal to length x squared plus length y squared. Okay, and so we have Pythagorean law in Rn. That's when x and y are orthogonal, then we have length of x plus y squared equal to length of x squared plus length of y squared. Okay. And yeah, that's 1 minute. We have a checklist of 5.1. So we define inner product in Rn, and length and angle and projection all in terms of inner product. Okay, so I guess we can have a bit of writing here. So xty equal to some I, xi, yi, and then you have length of x equal to square root of xtx, and distance is similar, and angle we have cosine theta equal to xty divided by length x, length y. Then we can have orthogonal being inner product equal 0. Then we have a projection. So alpha equal to, okay, I guess that is 10. And you can look up alpha and p from previously. So alpha equal to this and p equal to this. Okay. Yeah, so we have defined all geometry in terms of inner product. And we have explicit formula in terms of Rn because we have explicit formula for inner product. But later on we have we'll have a bit of more abstract definition of inner product. Okay, yeah. So that's for 5.1, and we will talk about orthogonal subspaces in next Monday. Okay. So yeah, see you on next Monday.